Hello, here we are for project Euler number 7, which is a prime number, and it is all about prime numbers. So here is the problem, and you got a bit of a spoiler there about the fact that we'll be using lazy lists. But the problem says by listing the first 6 prime numbers, that's 2, 3, 5, 7, 11, and 13, we can see that the sixth prime is 13. And then it just straight up asks us, what is the 10,001st prime number? So really, what it's asking is, find a way to get the sort of nth prime number where n is equal to 10,001. And to do that, there are so many ways you can calculate primes. A popular one is this sieve of Eratosthenes here, which is basically just like you cross out numbers as you go up. We're doing something a bit more basic just because I think it's easier to understand. But the point is that the solution I'm going to give is not the best, but I think it is one of the simple ones that you can think of. So how are we going to do this? As I said at the start, you kind of saw a spoiler that we'll be using a lazy list, and that's kind of the thing that we'll be using to store all of our prime numbers. Um, and then the algorithm is pretty simple. It's like a number is prime if for all of the primes that you've already found, it doesn't divide any of them, and we store them in a lazy list. So let's think about what is a lazy list. So it's kind of like an iterator, but it does a couple of things differently. So like an iterator, it can be infinitely long. Like an iterator, it is lazily evaluated. So that is to say that if I only tell it to evaluate the first 6 elements, it'll only do computation to evaluate those 6 elements. And we'll probably see that when we do like dot take 6 to check the code works later. Um, what else? But there are ways, of course, that it is unlike an iterator. So this is that it remembers things, and by that I mean if you've calculated what the second element is, and you ask for it again, it already knows the answer. It memorizes it. It's called memorization. And what this means is, unlike an iterator, you can traverse it more than once without destroying it. Because as you know, if I do like iterator dot for each print line, it'll print it all out, and then if I was to try that again, it won't do it. But the point is, it's lazily evaluated and it memorizes things, and these are the sort of key properties that we need to be able to implement the thing that I'm about to try and implement. So I guess let's stop talking about it and let's get right to doing it. So as I said, we shall have our primes as a lazy val of primes, and that's going to be a lazy list of ints. And we'll calculate this, like I said, by just thinking about is by thinking about is the number we'd like to add to the list actually prime. And to do that, we shall have a function shockingly called isPrime, and that's going to take an int like this, and it's either true or false that it's a prime. And the way that we can define this is we can look at our list of primes that we already have, and we're going to take the ones that we need to check that n does not divide. So naively, you might just think, well, I need to check all of the primes that are less than n like this. But this is actually doing quite a lot more work than we need to, because we only actually need to go up to primes that are less than the square root of n. So we only need to go up to primes that are where the prime squared is less than or equal to n. And the reason for this is that if you have a big number n and you divide it by 2, you've already checked kind of the opposite of what the sort of a factor would be. So we don't need to, once we've gone past the square root, we'd be checking things we've already checked. If there was a factor, we would have found it by then. So we don't really want to do that again. Okay. Not the best explanation, sorry. It's probably easiest with an example, so let me think of an example for you. Why don't we go with 30 as an example? So, as you know, 30 is actually just going to be 5 times 6, better known as 2 times 3 times 5. And what I'm essentially saying is that if we got it, that we don't need to go beyond the square root when we're checking numbers. So obviously, like the way that this actually work is we check that is 30 is n divisible is our n, which is equal to 30, divisible by 2. I would say yes, it is. It's 2 times 15, so it's definitely not a prime. But the point is that if we were doing this check and we went past the square root of 30, which is like 5 point something, we would end up checking 15, but we don't need to because we know we've checked all the numbers that are less than that would have given 15 as a factor. So if we try it with a natural prime, like 37, the square root of that's like 6.1 or something, isn't it? Um, you know that once you've got past 6, which I guess in this case is 7, you know that you would have already found those factors, so you don't need to go past the square root. Hopefully this makes a little bit more sense. Still not entirely happy with my explanation, so sorry about that. Anyway, now that we've got this sort of list of our wonderful primes, we just need to um, take the ones that we're actually considering, and we just need to check that for all of these all of these primes that we've taken, we just need to check that n does not divide them. And the way to do that in Scala is if we just do n, we take the remainder when we divide it by p, and we check that that's never equal to 0. Because if it's equal to 0 for any of them, it means it divides it, and it means that n is not prime. Great, so we've got a function that's called isPrime. Now, how can we use this to define our sort of lazy list of primes? Should have mentioned before that, like, I think if you want to know more about lazy lists, you're probably better off looking at the documentation than just listening to me. And I'll put a link for it. But we're basically just going to do something really similar to this, where we've got our we start with something here, and then, well, I suppose the Fibonacci numbers start with two things, but and then we're just going to recursively sort of define how to get to the rest of them. So let's see how to do that in like our world. And the answer is that we shall start with 2, because 2 is the first prime, and then the sort of append function, I guess, or prepend function for lazy list looks a bit like this. And then we'll start our lazy list from 3, because that's the next prime. Oh, that all types out nicely, good. And all we're going to do is we're just going to keep hold of the ones that are prime. And that's it. That's the definition. I guess as a micro optimization, like, we know that all primes are odd, so we can just take every other element, but, you know, take it or leave it. Similarly, like, we know that, or, well, I know, that all primes, like, one or more, sorry, that I know that all primes are either one more or one less than a multiple of 6, so you could do something else here, but like I said, I'm going to try and keep it simple, and maybe in that spirit I'll just not do that. Let's see if it actually works, right? So to see if it actually works, why don't we just try printing out the first 6 primes, kind of like in the setup of the question. So I guess we're going to take 6 of them. Oh my gosh. I did not press the button. There we go. We're going to take 6 of them, and then we're going to print them all out. So for each print line, print line, print line. Good. Alright, let's see what this does. Okay, great. So it looks like it's actually printed out 2, 3, 5, 7, 11, and 13, which is exactly what we want. Now all we need to do is ask it what the 10,000th and first prime is. And to do that, I guess we just do this. So 10,000th and first, except lazy lists at 0 indexed, aren't they? So the first, if I ask for the first prime, which is 2, I'd give it 0, wasn't I? So I think I have to take 1 off that. To actually get the 10,000th and first prime. I always suck at these like off by 1 things, so this might just not work. But you know, let's run it and see what happens. Well, it says it's this number. It's about 100,000. I'm somewhat inclined to agree. It seems like about the right sort of order of magnitude to me. Let's see if Project Euler agrees. Check. Check. Come on. Yay! Alright. Well, that's correct. I will try and think of a better explanation for why we only need to take stuff that's less than or equal to primes that are less than the square root of n. If you did get to the end of this, again, thank you for watching. We'll probably, like, I imagine we'll need more efficient ways to calculate primes in future problems. But hopefully this is, like, easy enough to follow for now. Also, I never actually formatted this. Well, that doesn't really do much, did it? Alright, see you next time. Thank you.